Yeah, like I said, it pleases me to know that Rance's family is joining us online today. We are also grateful to the CONCUR Steering Committee and the local organizers for this opportunity to celebrate Rance. Let me also personally thank Dwarkoff from the University of Calgary for his unwavering support in making this session possible. Thank you very much. So let me just give a few highlights about Rance. As was mentioned, he passed away suddenly and unexpectedly in his Arlington, Virginia home on March 27th. And his passing is, left a tremendous void for all who knew him. And he is survived by his wife, Karen Hardy, and his children, Matthew, Rachel, and Christian, his brothers, Will, Mark, and Tom, and their families, his parents, Rusa and Cliff Cleveland, and numerous friends and colleagues, to say the least. Rance was born in Maryland, Baltimore, Maryland, on July 18, 1961, and he spent his teen years on Signal Mountain in Tennessee. In 1978, he graduated from McCallie School, a boys' college prep school located on Missionary Ridge in Chattanooga, Tennessee. Rance received his BS degree in math and computer science, summa cum laude, in 1982 from Duke University. He received his MS and PhD degrees in computer science in 1985 and 87, respectively, from Cornell. His dissertation was on type theoretic models of concurrency, and his work was advised by Bob Constable. Here are just a few of Rance's highlights of Rance's 35-year professional career. He became a postdoc in 1987 in the UK at Sussex University with Matthew Hennessy as his advisor. In '89, he joined NC State, first as an assistant professor and later associate professor. To my happiness, he joined Stony Brook University in 1998, assuming the role of professor. And in 1999, Rance, along with Steve Sims, our first speaker of today, and myself, we've co-founded Reactive Systems, Inc. Steve will have much more to say about RSI. In 2005, Rance left Stony Brook and became a computer science faculty at UMD, the University of Maryland, College Park, where he remained until his passing. He also became, in 2005, the executive and scientific director of the Fraunhofer USA Research Center. From 2018 to 2022, Rance served as the NSF division director for the Computing and Communication Foundations division. One of the major divisions at the NSF. This was a tremendous service to the community that Rance performed. When he was finished at the NSF with his role there as division director, he became associate dean for research at UMD's College of Computer, Mathematical, and Natural Sciences. A hallmark of Rance's career was he was bestowed the honor of Fellow of the IEEE in 2022. A very well-deserved honor, to say the least. So now I would like to just highlight about a handful of Rance's work that he and I happen to both think was, very representative of his career. So the first one I want to talk about is the 1993 paper on the concurrency workbench, an automated tool set for analyzing networks of finite state processes expressed in Milner's CCS. It supports, and this is the beauty of the workbench, it supported a variety of verification mechanisms using a common foundation. And these verification mechanisms included equivalence checking, pre-order checking, and model checking. It was definitely a milestone, the concurrency workbench. And this was joint work with Joachim Parot and Bernhard. In 1990, Rance published as the sole author his work on-the-fly model checking for the propositional mu calculus. And so model checking is determining whether or not, in this case, a finite state system satisfies a property in the propositional subcalculus of the mu calculus, which is already still a highly expressive specification formalism. So in 1993, Rance and Bernhard again published a paper on a linear time model checking algorithm for the alternation-free mu calculus. And this was published in FMSD, a very respected journal in our area. And it's the first linear time algorithm for checking, for model checking, whether a finite state system satisfies an alternation-free fragment of the mu calculus, which we've already talked about. With his student L. Tan in 2002, Rance published evidence-based model checking in the CAV conference, one of our premier conferences in the area. And this paper presented a rigorous and widely applicable technique for explaining why finite state systems fail to satisfy specifications. This was really very interesting, groundbreaking work, and very important. Lastly, I think this is my last slide on his work. There was work done on what was called guided simulation and instrumentation-based verification. The work on guided simulation became the basis for a US patent that we received, Rance along with Steve and David Hansel of Reactive Systems. Rance and Steve and myself published a paper at a workshop in 2008 on instrumentation-based approach to verification. And these works found industrial application in reactive systems. So without any further ado, I would like to introduce our first speaker. I already mentioned his name, Steve Sims. Steve is CEO and co-founder of Reactive Systems. He's the co-author of the initial version of the company's flagship Reactus product suite and continues to lead its development. Reactus generates comprehensive yet compact test suites from Simulink and Stateflow models. Prior to the inception of Reactive Systems, Steve worked as a researcher at the Naval Research Lab in Washington, D.C. His work focused on the development of efficient system modeling and verification tools. He holds a BS in mathematical sciences from UNC and an MS and PhD in CS from NC State. Without any further ado, let's have Steve give his presentation on 2 decades of industrializing formal verification, the Reactus story. Steve, it's all yours.
Okay, thanks a lot, Scott. Share my screen here.
Let me stop sharing.
Oh, yes, you better stop yours first.
Okay, you should be good.
All right. Okay, yeah. Thanks a lot for that introduction, Scott. It's an honor to participate in this session, this memorial session for Rance today. I knew Rance for more than 30 years, so his passing was a tragic shock to me, as I know it was to many of you there. What I'm going to talk to you about today, as Scott alluded to, is Rance's leadership at Reactive Systems. So Reactive Systems is a company that Rance, Scott, and I founded in 1999 with the goal of making formal verification available in the commercial development of embedded software. This is actually based on a paper that Rance, Scott, David Hansel, and I wrote for the SPIN 2024 symposium, which took place in April, just a few weeks after Rance passed away. So this also was one of the last papers that Rance worked on, and it was for all of us, it was a great sort of chance to revisit the history of the company and look back on the past 25 years. So this is a picture of Rance outside our first office in Falls Church, Virginia. This was a few years ago in the 2000s. I was lucky. I got to intersect with several aspects of Rance's professional career. I was a grad student at NC State when Rance was there as a professor. He had a course on formal verification, which I signed up for. He was a great teacher. He had a real gift for explaining complicated topics very clearly, and these skills really helped us out in the company later on. But I really enjoyed his class, and that was where I met both Rance and was introduced to formal verification. So not only did that class inspire me to sort of want to go into formal verification, but it encouraged me to seek out Rance as a mentor, and I was very grateful when he agreed to take me on as a PhD student. So I got to work on research with Rance for several years during grad school. What I'm going to be focusing on, as Scott went over, I mean, his accomplishments in the research in this field have been quite impactful. And what I'll be focusing on is Rance's work as an entrepreneur. So he really believed in the work he was doing as a researcher, formal verification. And so in 1999, we decided to take the leap and form Reactive Systems and see if this technology would be applicable commercially. I'm just going to go through this really quickly. I think Scott did a nice job of outlining Rance's work prior to starting the company. I'll just give some sort of broad sweeps of what some of those themes were. So in general, he worked in formal verification where we have a system and a specification. We want to ask the question, does the system satisfy the specification? So we need to define what it means for the system to satisfy the specification, and then provide tool support for doing that check. So some of the themes that were referenced in many of those publications that Scott went through are how do we specify the system? He worked in process algebras such as CCS or CSP. He explored graphical notations for giving system behavior so that it might be a little bit more user-friendly. He investigated what are good ways to give the specification, like as a temporal logic formula for model checking, or using the same notation that we use for the system. And then, of course, how do we check for if a system actually satisfies the specification? So some of the types of checks he explored were model checking, equivalence checking, and pre-order checking. Then he pulled all of this together in the tools that he built. These are just some of the ones he worked on. The concurrency workbench, which supported process algebras, model checking, equivalence checking, pre-order checking. The concurrency factory, which explored graphical notations for specifying your model behavior. And the process algebra compiler allowed you to give a specification of your syntax and semantics of your modeling notation, and it would automatically retarget the concurrency workbench to support that new modeling notation. So these were some of the themes he worked on prior to forming the company, and this is the background that the founders had at the time we started the company in 1999. So let's just take a quick bird's eye view of the Reactive Systems history, and this will sort of give you a little bit of a summary for the rest of the presentation as well. So as I said, we founded the company in 1999. We applied for and received a small business innovation research grant from the National Science Foundation. So an important component of that project was to do a pilot project with Ford Motor Company. And I'll talk about that a little bit more in a second. We launched the first version of our product, which is called Reactus, in 2002. By the end of 2002, we had sold to 4 different companies, so we were happy with that. We were off and running. Over the next several years, we continued to work on Reactus and further develop it. In 2007, we opened a branch office in Japan and released our second product, which was called the Reactus for C plugin. We received the patent for our test generation technique that Scott mentioned in 2010. We launched 3 more products over the next several years. And then in 2021, we received ISO 26262 certification for our products. And that is a standard that mandates the development process for safety critical automotive software. So we've incorporated the company. We had a lot of ideas about how formal verification could help in the development of embedded software. So the first thing we wanted to do was try to find a partner that we could do a project with. So we started attending some more industry-leaning conferences. We met some engineers from Ford and discussed our ideas about the company with them. And they agreed to do a pilot project with us where we would together analyze a piece of their software using formal verification. And about that time, Ford and other automotive companies had started using a modeling language called Simulink, which is offered by the MathWorks, as a way of modeling their software. And so Ford gave us one of their models of a powertrain application to look at. It wasn't a huge model, but it wasn't a toy model either, corresponding to about 1,000 lines of C code. It had both Boolean and integer variables, so it was infinite state. What we did was hand translate that Simulink model into the input of an invariant checker to check some properties. We were able to uncover some dead code in that model and also some violations of Ford's modeling guidelines. So that caught Ford's attention and sort of gave us hope that we were on the right track. And it also had a couple of big impacts on the direction we would take. First of all, it sort of pushed us towards Simulink as the modeling notation we would support. And secondly, it opened us up to the automotive industry as a potential market for our products. So at this time, there was already a fair bit of software in cars, but over the past 25 years, that's just exploded. So today, cars are just have massive amounts of software, and all that software needs to be tested. So what is Simulink? So Simulink is actually 4 languages in one. It has 4 different components. So the first is a graphical synchronous data flow language with an example shown here. So you draw blocks on the screen, you have signals that connect those blocks. So for example, this logical operator block has 3 inputs and 1 output that it computes. It's just computing the disjunction of its inputs. In addition to logical operators, you have relational operators, mathematical operators, and then more complicated functionalities such as an integrator block. You can decompose your model into smaller parts by creating subsystems. Each subsystem will have some inputs that it reads and some outputs that it updates. State flow is a state machine notation. And you can basically create a state machine that you insert into a Simulink diagram, and that specifies the behavior for that subsystem of the model. You can insert a chunk of C code anywhere in your model. You can also insert a chunk of MATLAB code, which is the MathWorks matrix manipulation language. So it's a very complicated language, but it was one that was starting to be adopted at the time we launched the company. So our first sort of big decision point was, after this project with Ford, we saw that Ford and many other companies at the time were starting to use Simulink. So should we target our tools for Simulink, or should we go with the homegrown language? As I mentioned, Rance, Scott, and me, to some extent, have done a lot of research in what good specification languages were. So we had a lot of ideas about what a good modeling language would look like. So we had to decide, do we define our own for our tools to use, or do we go with Simulink, which is the language offered by the MathWorks? So some factors that went into that decision. It's a much easier sell if the company you're working with is already using the language. So Ford, for example, was already had Simulink models. So the selling point to them was, okay, you have a Simulink model, we can perform some checks on that model. It's a much easier hurdle to surpass than, okay, first translate your software or your Simulink model into the notation of our tool, and then you can perform all these neat checks that we're able to do. So if we can perform checks on a model that the customers already had, that was a big point in the favor of Simulink. Secondly, we were young at that point, just less than a year old startup. So companies were hesitant to sort of commit to using a modeling language that we came up with. They didn't know how long we'd be around. Many startups fail after just a few years. It's a big investment to develop models in the notation, so they were hesitant to make that investment on a company that was so young. So that was another point in favor of Simulink. And then at this time, Simulink was already starting to take off, even dominate in the automotive and aerospace industries. So it had a lot of momentum behind it already. And finally, autocode tools already existed. So from a Simulink model, with tools from MathWorks or other companies, you can automatically generate C code to implement that model. And that C code is compiled into an executable that becomes a part of the application that's deployed. So if we target Simulink as our modeling notation, we're tying in directly to the tool chain that customers are using to actually build their executable that goes in the cars or whatever application they're building. So as you can see from all these points, we decided to go with Simulink. And so in our phase 2 SBIR project, we sort of pivoted to using Simulink as our modeling notation. So we had that choice under our belt. So the next question was, what kind of checks do we want to offer? Again, we had a bit of a pivot. The reason for this pivot was that the models we were seeing were just too big for the formal verification techniques of the time. So we had to somewhat scale back our ideas about the functionality we would offer as well. So we had to adapt again. The first type of check we decided to do was basically runtime error checks. So are there any divide by zeros? Are there any out of bounds array indexing? Are there any overflows? Is there dead code in the model? So these are types of checks that we were able to perform for much larger models than, for example, applying a model checker. The other benefit of this approach, or searching for runtime errors, is that you don't have to give a specification. So there's an implicit specification that your model shouldn't contain any of these types of errors. But the user of our tools doesn't have to formulate, for example, a temporal logic formula to check the property they want to check. So this is more of a push button approach that's a little bit easier to apply. You have a Simulink model, you push the button, and Reactus will tell you if it finds any runtime errors. The second initial functionality we offered was a automatic test suite generation. So the idea here is that you have a Simulink model. So our tool will take that model, analyze it, and then automatically produce a test suite that comprehensively exercises the behavior of your model. So we want to generate test suites. So what is a test for Reactus? It's just going to be a simulation run of a model. So here we just have a small Simulink model that has some inputs that it reads and some outputs that it computes. So a test is just going to be an execution run of the model where we feed in some inputs, capture those inputs in our test. The model computes the outputs. We capture those outputs in our test. Let me take another step, feed in some more inputs, calculate, compute the outputs, capture those. Feed in some more inputs, capture the outputs. So it's just a simulation run of the model where we're capturing the inputs and outputs. So Reactus Tester, to recap, it's going to take a Simulink model as input, automatically generate a test suite. That test suite is going to consist of a set of tests. For each test is a simulation run of the model. That is a sequence of steps where at each step, we capture the inputs that we fed into the model and the outputs that the model computed. Okay, so what are our goals for these tests, and what can they be used for? The most important goal is that we want to maximize coverage. We want these tests to exercise as much of the model's behavior as we can. We want them to be thorough, so we maximize the chances that we uncover errors when they execute. But at the same time, we don't want these tests to take forever to run. So we want to avoid redundant test steps whenever we can, so that these tests can execute quickly. So while we want the test to be comprehensive, we also want to have as few overall test steps in the test suite as we can. Then finally, as I said, we want to store both the inputs and outputs to make it more convenient to do different types of things with these tests. For example, just by generating these tests, we can uncover runtime errors that I mentioned previously, divide by zeros, bad array indexes, overflows. So just by doing the very comprehensive simulation that we're doing to generate these tests, we have a good chance of finding runtime errors in a model. These can also be used for regression testing. So let's say you make some changes to your model, and you want to check and see if those changes impact the externally visible behavior of your model at all. What you can do is generate a test suite from the original version of the model, run those tests on the new version of the model, then any differences in the behavior or any differences in the outputs that were calculated by the new version of the model that are different from the original version of the model will be flagged. Similarly, if we want to compare C code, so I mentioned the code generator, let's say you generate code from a model, you want to see if that code behaves in the same way as the model, you can generate a test suite from the model, run those tests on the C code, and flag any differences in the behavior. So I said that our most important goal is these tests be comprehensive. So how do we measure that? Well, Reactus uses a set of coverage metrics. And to describe what that is, let's look at a logical operator block. So in order to thoroughly test this block, we want to make sure that this block evaluates to both true and false. So that's called decision coverage. But that's not thorough enough. We also want to make sure that we've seen tests where each of the individual conditions that come into that serve as inputs to the decision. We want to make sure each of those is true and false. And then finally, we want to make sure that each of these inputs independently affects the outcome of the decision. This is a metric that's called modified condition decision coverage, or MCDC. And it's mandated by that ISO 26262 standard that I mentioned earlier for any safety critical automotive software. It's also mandated by the DO 178C aerospace standard. So both of those standards say that you need to test your model to this MCDC level to make sure you've tested it comprehensively. And Reactus both tracks all of these coverages in addition to other metrics and generates tests based on these objectives. So how do we generate these tests? We use a technique that we call guided simulation. Scott mentioned this in his introduction as well. What is guided simulation? So to generate tests for this model, we're first going to identify all the different coverage targets in the model. So we're going to look in our model, see what the logical operator blocks are. Say for every logical operator block, there's going to be some decision targets, condition targets, and MCDC targets. So we identify the coverage targets. We then simulate the model. As we simulate the model, we capture the inputs and outputs, as I had showed earlier. We track the coverage. We look at which coverage target has been exercised and which has not. And then finally, the guided part of guided simulation is that for every simulation step we take, we want to look at which coverage targets have been exercised and which have not. We want to pick a target that hasn't yet been exercised and try to pick inputs that's going to cause that target to be exercised. So how do we pick inputs? That's the hardest part of guided simulation. So we have two main approaches that we use for picking the inputs. The first is using SMT solvers. So we identify an uncovered coverage target. We then formulate an SMT constraint such that if we can solve that constraint, the result will give us the inputs that are going to cause that target to be exercised. We started out with some homegrown solvers, and then in 2016 switched over to using the Z3 solvers offered by Microsoft. If we're able to do this, this is great. We're gold. We can generate a good test suite that covers our model if we're able to do this. But remember how complicated Simulink is. It has the data flow language. It has the state machine language. It has C code in there. It has MATLAB code in there. It's a very complicated modeling language. So we're not always able to formulate these SMT constraints in order to get our inputs. So in the cases where we're not, we have to fall back on option 2, which is to generate random input values. In selecting these random input values, we do take user constraints into account. So for example, a user can specify that a particular input should be within a given range. Then we also have a collection of heuristics that we employ to improve the likelihood that we cover more targets with our random searches. One example of that is shown here. So let's say we have a state flow diagram that has a state A and a state B with the transition from A to B. Now, if we've covered state A but not B, then in order to try to cover state B with random search, we first start our searches from state A. It's a simple idea, but it can help improve the probability that we're able to actually cover state B in the cases when we're not able to use option 1 SNT solvers. So our first Reactus release was in 2002. It included Tester, as we've been talking about, and Reactus Simulator, which is a model execution environment. If Tester finds an error, it's very helpful to be able to execute that error to understand exactly what's going on as that error occurs and diagnose and debug the problem. So Simulator is really a full debug environment for simulate models. You can execute tests that have been generated by Reactus Tester. You can control your stepping with these controls. And one thing that's nice is that you can go backwards in a simulation run. That can help in diagnosing what's going on before the actual error occurred. You can hover over any variable to see its current value. Unexercised parts of your model are highlighted in red. You can set breakpoints. You can open a scope to see the value a variable has taken on since the start of a test. So it's really a full debug environment for simulate models. In 2003, the next version of Reactus, we launched Reactus Validator. What this allows you to do is check if a model satisfies its requirements. It allows you to formulate requirements that your model should meet. Reactus will then go to a search to see if it can find any violations of those requirements. If it finds a violation, it's going to give you back a test. In this test suite, you can execute to understand the exact sequence of events that leads up to the problem. So the requirements are formulated by giving assertions and user-defined targets. An assertion is just an expression that should always be true. If it ever becomes false, and that means the requirement has been violated. User-defined target allows you to specify a scenario that you want to make sure you're testing in order to properly stress the requirements you're checking. Reactus supports two notations for giving assertions and user-defined targets. You can either give them as C-like expressions or as simulate state flow observer diagrams. How do we check it, or how do we look for violations? We use the guided simulation technique that we described for generating tests. So, of course, this means that we can find bugs, but we can't necessarily prove their absence. So we might find cases where a requirement that you've specified is violated, but we can't say for sure in most cases that the requirement can never be violated. In addition to guided simulation, we do have some basic static analysis, in which case we can do a sort of a full proof and sort of prove that a coverage target is unreachable, or prove that an assertion can never be violated, and give a nice green check mark if we're able to show that an assertion can never be violated. So in addition to the base Simulink products, we've had several products that we've launched over the years. So what we've been talking about so far was the original product, Simulator Tester Validator for Simulink models. In 2007, we launched the Reactus for C plugin. This allows you to drill down into the C code portions of a model. I mentioned that there were 4 components to Simulink, so this allows you to do the same types of testing for the C parts as the rest of Reactus supports for Simulink state flow. The Reactus for C standalone version, this allows you to automatically generate tests from standalone C code that's not in any model. So you can apply this directly to a C program outside of any model. You can generate tests, check requirements, and do the same types of things you can for simulate models. Model Inspector is a lightweight viewer for simulating models and testing artifacts. And the Reactus for EML plugin does the same thing for embedded MATLAB code that the C plugin does for C code. So if somebody sticks embedded MATLAB code in their model, this allows Reactus to identify the coverage targets within that embedded MATLAB code, generate tests to exercise those targets. About out of time, so I think I'm just going to skip this slide. So to recap, 1999, Rance, Scott, and I saw an opportunity to possibly commercialize formal verification, bring it to the development of embedded software in a commercial setting. We had a little bit of a pivot from actual formal verification to more of a bug finding approach where we can't prove the correctness of the software we're working with, but we can find bugs in it. We can find runtime errors. We can help with checking C code against the model. We can help with regression testing. We can help checking if a model meets its requirements. Reactus is currently used by many companies around the world, mostly in the automotive industry, some are aerospace. So we've been very happy with the success of the company. I think the company is one of Rance's legacies. So it's something I know that Scott and I are proud of, and I know Rance is proud of. So I really appreciate the opportunity to share a little bit about the company with you. And thank you to the CONCUR organizers for organizing this session for Rance. It meant a lot to me and everybody at the company. So thank you to the organizers and thank you to you for your attention. Thanks.
Are there any questions here in the audience for Steve? Because if not, I'll pass the word back also to Scott.
Actually, our next speaker is Bernhard. I do not think he is here. He was feeling ill earlier today. So I think we were going to go to his pre-recorded talk. Zawakar. Okay. Yeah, there we go.
Welcome to my talk in memory of Rance Cleaveland, who very unexpectedly died this spring. It was a real shock to all of us. Nobody would have expected that this could happen. Rance was a very close friend. Here you can see him at the celebration of his 60th birthday in Cyprus. He was very lively as you know him. You see it here in action. And it was wonderful to hear the old stories from our times in Britain. Despite the far distance, he lived in Maryland and I am Dortmund, we were in contact and we were supposed to meet again at ETAPS in April this year. Then, just a week before, he died. But let me start at the beginning. It all began in Edinburgh and with the Concurrency Workbench project. I had gotten the offer from Robin Milner to join the Concurrency Workbench project in October. And just for preparation, I went there in June and participated in a few project meetings. This was really a hard time. People were discussing a lot of things I never heard about. Interleaving models, bisimulations, temporal logics. This was not my world up to now. I came from program analysis, abstract imitation, and so these notions really said little to me. Despite that, I will never forget that Robin praised the Canelake-Smolka algorithm as a wonderful algorithm for determining bisimulation. And he mentioned that it should be my first duty to implement that when I would come to Edinburgh in October. the time in June was very hard for me. I had all these different notions. Everything was strange to me, and it was pouring like hell. In fact, when I came in October, I was totally surprised to see Arthur Fleet. I had no idea that there would be such a big mountain just next to the city. But I was very lucky. Rance was there. He came from the state. He worked to an extent also new. He worked since a few months with Matthew Hennessy in Sussex. And so the two of us were the strangers in Edinburgh, and we went for dinner together. And this was very good to calm me down and to look with more optimism to my time in the concurrency workbench project. And the optimism was justified. We had a wonderful time in Britain together, 2 years working on the concurrency workbench project. The concurrency workbench project was real fun. We developed one of the first tools for the automatic verification of concurrent systems. We worked together with other groups, for example, in INRIA. It was a really lively discussion. We met for the first CAF in France and so on. This was really a great time. And not the least, the concurrency workbench was a real boost of our careers. Both of us became professors very soon in our home countries. The entire atmosphere was extremely inspiring. And so Rance and I developed new things like, for example, the linear time model checking algorithm for CTL, or more generally the alternation-free model new calculus. The first theoretical contribution I made to the concurrency workbench was a characteristic formulae. So what are characteristic formulae? Characteristic formulae were meant to characterize a process up to bisimulation. Or more precisely, the characteristic formula of a process M should be satisfied by another process if and only if it is bisimulation equivalent, as you can see indicated in the red box. Characteristic formulae open another way of checking behavioral relations. You could simply transform a process into the characteristic formula and subsequently model check for bisimulation equivalence. And what is nice is you couldn't just do that for bisimulation, but for many other pre-orders. And this is something Rance and I published together in '91 at ICLB. The fun thing is that this way doesn't have any computational overhead. It's the same complexity as the, let's say, tailored algorithms for the respective relations. On the other hand, it is also not more efficient, so it's not in this sense really fruitful, but it is a very elegant way to characterize things. Later on, we discovered, however, that there's an additional feature. With characteristic formula, you suddenly could check for bisimulation of regular systems, this was the kind of systems we normally deal with infinite systems, or in this sense, context-free systems. This was possible because I developed in '92 an algorithm for model checking context-free systems for the alternation-free model mu calculus. And in fact, the characteristic formulae we construct are also part of the alternation-free mu calculus. Let me now come to the more technical part of the talk. Of course, at CONCUR, bisimulation is a well-known notion, but okay, let me briefly summarize. This is a symmetric relation between states of a process or transition system, and two states are related if they can mutually simulate each other. That means every step the one can do can be done by the other, and the result will again be bisimulation equivalent. This is this recursive definition as shown in the two items here. The other important ingredient for the rest of the talk is Hennessy-Miller logic. The logic designed to characterize branching behavior. The idea was to introduce two new quantifiers which tell something about the future behavior in a certain state. So there's the diamond modality that says, oh, in this state, there must exist an A move, which ends somewhere where the formula phi holds. And of course, there's a dual, the universal quantification that whenever I do an A move, then there should be, then the property phi should hold. This logic has this new power, these new two quantifiers. On the other hand side, it's very limited because it can only look in finite depth into the system behavior. Yeah, because when you go through the potential behavior, you look at the various actions you can do. You can only look as deeply as you have nesting of these new quantifiers or modalities, as they are called modalities, in the formula. On the other hand, Hennessy and Miller showed a very important theorem saying that whenever you have two bisimulation equivalent systems, then they satisfy exactly the same formulas in Hennessy-Miller logic. This is one direction, the other direction. And if they are not equivalent, then there is a distinguishing formula in Hennessy-Miller logic. Yeah, the second statement is, however, only true for finitely branching systems. So for systems where one state has only finitely many successors. Let us compare now Hennessy-Miller's result from the idea of characteristic formulae. The Hennessy-Miller say every two processes can be separated by Hennessy-Miller logic formula if they are not bisimulation equivalent. But of course, if you have different candidates, you need different formulae. In contrast, the characteristic formula you see here in the red box is a formula which is independent of the processes to compare with. So if you have the characteristic formula of a process, then it works for any process, and the satisfaction of the formula guarantees bisimulation equivalence. This much stronger property cannot be true for Hennessy-Miller logic, because Hennessy-Miller logic can only look finitely deep into the computation tree, and we are talking here about regular systems, and there are potentially infinite behaviors. Let me now come to the main result of this talk. We have just seen or understood that Hennessy-Miller logic is not expressive enough to describe or specify characteristic formula of a process, just because it cannot specify depth. But, and this is what I want to show today, it is sufficient to specify an invariant, a property which always holds, which is sufficient to characterize a process up to bisimulation. That this is possible relies on the following observation. It is possible to decompose the specification into two parts. A characterization of bisimulation equivalence classes and the transition relation. The upper part you see here, the state formulas, are exactly the characterization of the equivalence classes, and this lower part on the right are the characterization of the transition relation. And putting them together is sufficient to formulate the invariant we need. And the overall characteristic formula has then the pattern which you can see on the very left. That is an always property, a universal property, which makes sure that this invariant is applied everywhere. In addition, there's a small, let's say, initial property phi 0, which you also need, a start property, but this property can easily also be specified in Hennessy-Miller logic. So the only thing what you need in order to make Hennessy-Miller logic, let's say, powerful enough to characterize bisimulation is this universality. What I like with this form of decomposition and this approach is that it resembles classical patterns which reappear all the time. So one thing is the predicate abstraction. There's a predicate, this formula, this Hennessy-Miller logic, which characterizes bisimulation, which very abstractly characterizes those classes, the equivalence classes, but it's not universal. As I said, it is only valid in the context of the transition system or process we are currently considering for constructing the characteristic formula. So this is the classical idea of predicate abstract. We describe it by means of this Hennessy-Miller logic formula. And the other thing is the transition relation is something local. You can look transition per transition, or to be honest, it's not the individual transitions, but it is the transition potential of the state. You can go from state to state and look at the potential of transition. Perhaps the analogy I mentioned now is not so obvious for everybody, but I mean, I grew up with program analysis, with Floyd, with Horn, these kind of things. And one thing which I found fascinating is this localization. You want to prove a global property, you want to verify a program, and you reduce it to local consistency between two states along transitions by means of weakest liberal preconditions. You just look at the single step about kind of covering one assignment, and you just check consistency in this local fashion. And in some sense, the transition description here, the relation we describe here, the formula, is exactly doing the same. It just locally looks at a state, its potential, characterizes what that is, and doesn't care about the global environment. So, and together with the state distinction up there, this is sufficient to characterize the entire process up to bisimulation. This is something which I find elegant and very intriguing. As soon as we have all the state formulae and the transition formulae, we can compose them in a slightly tricky way, indicated on the left in this box there, and obtain the characteristic formula. But let us now go into more detail. So let us first define what these state distinguishing formulae are. In fact, they are very formally defined, and at the first place, you don't really know why they should work. I mean, these are sets of formulae which satisfy three conditions. The first one is not two of them can be valid at the same time. The second one is every of these formulae has to be satisfied by at least one state of the considered transition system or process for which we want to construct the characteristic formula. And last, two states that satisfy the same formula from this set of distinguishing formulas, then they must be bisimulation equivalent. I should mention here that we are not the first to try to define characteristic formulae in this decomposed fashion, so with state distinguishing formulae and transition formulae. And Clark and his colleagues did that already in the 80s, and the only real difference is the way how they define distinguishing formulae, which is very engineered, I would say. It's very complicated to derive the properties you need, and they didn't have the elegance of our approach, which essentially gets all the properties you need for free by referring to the Kanellakis-Smolka algorithm. So let me just briefly explain the algorithm of Kanellakis-Smolka again in a very simple fashion, and then show you how to construct those formulae. So how does Kanellakis-Smolka work? You have an LTS or a process, and you successively refine a partition. You start with the universal partition where everybody is related, and then successively refine it by means of splitters, here BA. And how do you do that? Whenever you have a class, you look at the transition potential, and the splitter is one of those possibilities. So a splitter BA would say that there is a potential to make an A move to end up in B, and you split the source class, the source equivalence class, in two parts. The states which have this potential, and the rest. That's all. And you proceed like that until you don't find any splitters anymore. And it is a nice result that when you terminate, what you have done is you have the causes bisimulation equivalence. Let me now briefly explain with an example what this has to do with our construction of these state formulae. We just look at this example with these 5 states in the upper left corner. And in the middle, you see how the algorithm of Candelacre-Smolka could work. So you start with the coarsest partition you can have. All states, all 5 states are in a class. You look for a splitter. In this case, it can do an A splitter. I mean, if you start with a universal partition, I mean, you can only speak about can do or not because the target is, you have only one possible target state. And if you do that, you're just distinguishing can do A and not being able to do an A. You get the partition refined into classes, 3, 4 for the ones who cannot do an A move, and 1, 2, 5 for the states which can do an A move. Okay, and then you can continue. You can see, can I refine further? And here in this case, it's pretty easy. You don't even have to look at the target states so much. So it's a very simple example. You can now look at the states which can do an additional A move. Essentially, you check again, okay, if you do an A move, can you do another A move? Next step. Yeah, this is the formula you see on the top arrow, which goes to the blue 1 node. And if you take that splitter, you refine further, because only the state 1 has the potential to make 2 A moves, whereas 2 and 5 cannot do a second A move. So, and okay, I don't want to go further into detail. After these 2 steps with these 2 splitters, you reach already the courses by simulation equivalence class, equivalence relation. Okay, and the result is here now illustrated with colors. So you have the 1 is a class with just 1 state, the state which can do 2 A moves, and 2 and 5 and 3 and 4 are both built an equivalence class on their own. Okay. The fun thing now is that taking just these, let's say, these labels of the graph in the middle, as these documentations of what you have done in the Candelacre-Smolka algorithm by just formulating the splitters as temporal formulae, that you just take those labels as the set of distinguishing formulae. This works fine. And the good thing is, because it's derived from Candelacre-Smolka, which is known to just produce the coarsest bisimulation equivalence relation, the proof that this is that to get this way a set of formulae which satisfy 1 to 3 is very, very straightforward. This looks very nice and very elegant, but unfortunately, the formulae grow exponentially, with the depth of refinement. Whenever we refine a class further, and you may end up in a refined class, then it may potentially lead to a doubling of the size of the formula. Let us now nevertheless come to the transition formulae. This is also a very nice approach, and it's based on a pattern which was originally presented by Susan Graf and Joseph Sivakis already in '83, which characterizes nicely the branching behavior of individual states, and they used it back then to derive characteristic formulae for finite processes, so processes which are essentially trees, and they could collapse them up to bisimulation. Intuitively, it's a very simple pattern. I mean, when you want to describe the potential of the transition potential of a state, you describe what it can do in an automata. So the formulas say you must be able to provide that. This is the diamond properties. And on the other hand side, you should exclude properties which are undesired, and this is done via the box modality. So the left-hand side is for the requirements, what has to be done, and the right-hand side constraints to the potential which the process really has. And the overall pattern looks as follows. You have one state distinguishing formula. It's a left before the implication error, and it says whenever I'm in one of those states, as a state which satisfies phi, then I know subsequently, and then this formula holds, and this kind of dives in at the right form and produces essentially exactly the right transitions and the right target states of the transitions. So this pattern is well known. It's the same pattern which also Clark and Adita used and I used. So this is the pattern. This is the way how to describe the transition potential of a state in temporal logics. Good news, this pattern is harmless. So there's only a low polynomial growth. It grows with number of states times number of transitions of the process for which you are deriving a characteristic formula. But nevertheless, even though this lower part is cheap, if you say, altogether we get an exponential behavior because, I mean, the state formulae grow exponentially, which is very sad. My talk today is about the expressive power of Hennessy-Miller logic, and that it is sufficient to express those invariants. So what I'm telling now is a bit at the side, but of course we just saw the exponential complexity, so it makes sense to look at an alternative approach which doesn't have that high complexity. The idea is comparatively simple. You take exactly the pattern which we know from Graf and Zifakis, but instead of having an implication, you formulate an equation system and consider the corresponding maximal fixed point. So this is just a one-to-one description, and where you had formulae first, the state formulae, so for example, the xj would be otherwise the state formula description of the target, and the xy is of course the source state, and so on. Instead of having that, we just put the logical variables there and make an equation for each state. Each state is represented by such a logical variable, and the right-hand side is just the characterization of its transition potential. And if we compute then simply the maximal fixed point of all this, then we are done. Then we get a characteristic formula. And in fact, you can prove by simulation equivalence simply by model checking against x0, the initial variable. So this is a very simple approach. And when you look at it, we just saw that this cannot grow exponentially because, okay, we have n variables at most, and on the other hand side we have a construction which is also small. So we have here something which is low polynomial. In fact, it's again number of nodes times edges of the underlying transition system. So this is very nice. Okay, and what does it tell us complexity-wise? Yeah, we could have something which is not exponential. This construction is at the first sight a bit, not quite superior in all times, because you could say, okay, we have here the number of states of the process we are investigating. In the other cases, we are exponential in the number of bisimulation equivalence classes. What happens if this is an enormous transition system with a very small bisimulation quotient, also very few bisimulation equivalence classes? Then we have also an answer, of course. Take this process and first minimize it with Canellacos-Smolka again. So you have also here a Canellacos-Smolka application. You take your processes, apply Canellacos-Smolka, get your smallest or your bisimulation minimized representation, construct the equation system, and then you are in the best of both worlds. You have a recursive definition which is low polynomial and which can even very efficiently be solved. This result very much shows the power of recursion and recursive definitions, and that algorithmically this recursive power is not even that problematic, because you can very easily solve these things. Model checking alternation-free model calculus is, as I mentioned before, something which is also linear in the size of the transition system as well as linear in the size of the formula. So the whole thing is very nicely computable. So let me finally come back to the main topic of my talk, which was not complexity. Of course, complexity is always a major issue when it comes to algorithms or also to specifications. If the specification size explodes, I mean, what does it help? And of course, it is nice to see that the approach I developed 30 years ago is very competitive. No, what I wanted to show here is the expressive power of Hennessy-Miller logic. Hennessy-Miller logic is sufficient to fully characterize by simulation equivalence in terms of invariance. Yeah, so you just need the invariance property, you have to apply it everywhere, but then you just need Hennessy-Miller logic formulas. And this is something which I find very interesting. And this shows the power of basic concepts. Yeah, I mean, one part here is the decomposition in state properties and transition properties. Yeah, if you have the global transition formula, which is easy, and then you can just describe by means of Hennessy-Miller logic also the state distinguishing formulae. This together is already sufficient to arrive at this result. And I like that a lot because it shows the power of something like predicate abstraction. We don't need to know always everything. It's sufficient to just know enough. And localization, it's sufficient to check or to describe the transition potential state by state. We don't have to do something global. These kind of two properties are very nicely illustrated here. And in the middle of all it is, of course, the Canellacos-Volga algorithm, which helped us to elegantly derive the state properties. Let me finally explain why did I choose this topic. Of course, Rance loved model checking, process algebra, temporal logics, and we worked on that together over the years in the concurrency workbench. But this was not the main point. The main point was a mindset. Rance and I were always discussing exactly in the fashion I tried to illustrate in my talk. We were asking the question of adequacy. And adequacy has many facets. Adequacy for what? And I hope I could convey some of this mindset. I really miss these discussions with Rance, and it is hard to accept that these discussions will never happen again.
So as this was a pre-recorded talk, let's
Yeah.
move to the final speaker. So Scott, do you want to introduce ASIO?
Sure. Can you hear me okay?
Yes.
Yeah, so Ezio he earned his PhD in 2009 from the University of Camarino. He was from 2010 to 2012, he was a postdoc at Stony Brook, of all places. And in 2012, he joined TU Wien in Austria, where he is now, Vienna. Let me get right to his talk title, Failure Analysis in CPS Simulink Models. Ezio, without any further ado, I'm so glad that you're here, and I know it's late for
Yeah,
you.
so
Please.
I will share. Yeah, I will be fast and share the screen. Give me a second. Yeah, share. Okay, you see my screen. Give me a second. I just find the play from start. Okay. Okay, welcome on my talk on failure analysis in CPS Simulink model. This talk is in memory of Rance Cleaveland, and on a personal side, I met Rance for the first time 14 years ago. I was a postdoc at Stony Brook. My research was funded by an NSF expedition computing grant called CMAX on next generation model checking and abstract interpretation with a focus on embedded control and systems biology. And this project was coordinated directly by Edmund Clark, and Rance was one of the PIs. I remember the very inspiring for me that I was very young, inspiring discussion with Rance, his kindness, his smile, and his dedication to research, and also in particular the interest on the topic of verification testing of cyber physical system. And for this reason, I choose the topic that I'm going to present today. In particular, I start with cyber physical systems. So they are embedded, they consist of embedded computational units that are tightly integrated with physical processes that they monitor and control, often with some feedback loops where the physical processes affect the computation and vice versa. These systems are also called safety critical because, as you can see from the video, a failure, an hardware or a software failure can be the cause of loss of a life or of an injury. For this reason, ensuring the safety, security, and reliability of cyber physical system is crucial and involves rigorous testing, validation, and monitoring. So model-based design for cyber physical system is a systematic approach to engineering complex systems that integrate both physical processes and computational elements. In model-based design, a cyber physical system is represented as a set of mathematical models that integrate both the differential equation described in the law of physics with the state machine describing the software behavior controlling the physical process. Common modeling languages for describing cyber physical system are Simulink and Modelica. Tools like Simulink provide the possibility to simulate both the physical and the cyber component of a CPS. Furthermore, Simulink provides also the possibility to automatically generate executable code from the models, and this code can be used to run the system. And this reduces the potential for human errors and speed up also the development process. Model-based design also facilitates the extensive testing of the system before the actual system is developed. And one way is to simulate the system. Simulation can be run using different parameters and inputs, test all the part of the system under various operational conditions. Okay, Simulink, the Simulink tool is designed around the data flow paradigm. Simulink provides a drag and drop graphical environment where the engineering can select blocks that represent operation or stages of the process that they want to model. Each block has input and output, and data flows between these blocks along lines and connectors. So this visual approach is aligned with the data flow modeling principle, where the focus is really on the flow of data through the system. Now, once we have the model in Simulink, this should undergo through a rigorous testing and should be and the simulation should be tested against some requirements, and usually the classical logic that is used in cyber physical systems to express requirements is the signal temporal logic, that is a formalism used to describe properties of real value signal over continuous time. So basically, signal temporal logic extends the linear temporal logic with real-time constraints and predicates over real value signals. The interesting things about signal temporal logic is that it provides two semantics, so two different interpretations. It's called the Boolean qualitative semantics. They basically provide a Boolean verdict, a yes or no verdict, whether the simulation is satisfied or not by the specification. But what is more interesting for testing and for classification analysis is the quantitative semantics. The quantitative semantics provides as the verdict a real value that specify with the sign whether like the system satisfied or not. So if it's positive, is satisfied. If it's negative, is violated. And with the magnitude, they specify the distance. So how much the simulation trace is satisfying, or how much the simulation trace is violating the specification. This distance is used in testing and classification analysis for search-based testing. So the idea is to explore the input space or the parameter space and use some kind of heuristics, for example, particle form optimization or genetic algorithms to search in the space of the input to find what is the input that would, for example, violate the product. So this real value semantics provides like a fitness function for a global optimization. So in order to be tested extensively, we need like a test fit, so a set of tests. In this case, the specification is translated into a monitor, and the monitor plays the role of the oracle. So it will tell us whether the test is passed or is failed. But one important issue when we do testing is also to understand when the test is failed, what is the cause of the failure of the test. So in particular, we are interested to identify, to localize inside the Simulink model what are the blocks that are responsible for this failure. This is very challenging for two reasons. So the model that you saw before is with only few blocks. In reality, is not does not represent the real size of the model. In fact, this data flow modeling of Simulink is hierarchical. Every block can be expanded into sub-blocks and so on. So the size of these models is very large, and it comprises several hundred of signals to be observed. The other problem is the scope. So in data flow modeling in Simulink, every component continuously active and interact with all the other components. So this means that the standard techniques like spectrum-based photolocalization that is used, for example, in classical software engineering to identify difference between the block executing via passing and failing test. In this context, does not properly work. So in this talk, I will present briefly, not in detail because there is not much time, two approaches that I have developed with a research team in the last 5 years. There are also other approaches that, for lack of time, I am not able to show. But the first one is called CPS debug, and the second one is called STL guided fault localization. Let's start with CPS debug. CPS debug is a tool for automatic failure explanation in simulated mode. It consists of three different steps of stage: testing, mining, and explain. The first test consists in collecting the information about the internal behavior of the system under test during the test. I mean, once we exercise the model using the test suite. The second step consists in the mining, so to learn a model of the correct behavior of the system under test. And the third stage, it consists in explaining. So the idea is to determine, using the model that we have learned about the correct model, what are the likely causes for a failure, and to report them in a graphical way. So let's start with the testing. So the idea is that we start with the STL requirement, or set of STL specification that we want to test. We instrument the Simulink model automatically in order to log all the signals generated all the signal generated internally, so all the internal signals of the Simulink model. And the STL specification is translated into a monitor. And then what we do is that for every test, test consists in basically a sequence of input that we provide to the model. We monitor whether the Simulink model satisfy or violate the property. And then we collect all the traces from the passing test, and we collect all the traces from the failing test. Here is an example. So we have the blue one are the traces from the passing test, and the orange one are the traces from the failing test. And if we look at inside the trace, we are going to see basically a column that represents the time step of the simulation. And then all the other columns represent the internal signal values at different time steps. Once you've done that, we use the traces only from the passing test, and we try to learn properties. We try to do something called property mining. In particular, we are representing property in two different ways, either STL formulae, or timed automata. So we use two different tools to monitor, to learn these properties. One is called DICON, and the other one is DKT. So DICON is able to learn a relation between the signals, and also in particular program invariant. So program invariant are properties of the form of globally a certain signal is, for example, less than a certain value, or is less of another signal and plus a certain value. And the other kind of property that we learn, we can use TKT, that it's a tool that is able to learn timed state-based properties, behavior of stateful components. Basically, it learns a timed automata. So that basically record the relation, the clock relation between different events that occur inside the Simulink model. Once we have learned this set of properties, what we are doing is basically we take the traces from the failing test and we use the properties that we have learned to monitor against the traces from the failing test. Then what we do is when we see that there is violation, we use a tool called trace diagnostic to identify the time interval that is responsible for such violation. We cluster all this time interval together and we try to map inside the Simulink model to identify the blocks that are responsible for this violation. So this is the first step, basically, the property that we learn. And we are going to get, once we monitor, we're going to get some information about what are the signals that are responsible for the violation, and what are the time steps in which the violation occurs. And this is visualized in this way. Then what we do is basically we cluster this information together by time, according to the time in the event, and we are going to obtain something like that. So basically, this is the Simulink model, and these are the blocks that are found responsible for the violation, and these are the properties and in this case in STL, that are responsible for the violation, that are violated. So these are the properties were found to be correct in the passing test, but were found to be violated in the failing test. So we, for this work, we perform a small size validation. We consider standard benchmark from Simulink. One is called automatic transmission control. The other one is the aircraft elevator control system. And what we do is basically we inject the fault manually inside these models, and then we try to see whether we are able to explain the fault that we have injected, and whether we are able to localize the blocks where we have injected the fault. And also we measure the reduction in the number of signals that we need to we provide back to the engineering in order to explain where the fault occur. Okay, but now I present another approach, because one of the problems that we saw is that CPS debug is very good in providing explanation, but it's not very efficient because it requires several steps. Plus, another problem is that sometimes we have a shortage of failing tests, and we don't have enough tests to accurately localize the faults. So our idea is to basically use failing tests and start from the failing test, try to synthesize passing tests that are very close to the failing test to improve the fault localization. Let's see how does it work, the test synthesis. So we start from an initial test suite, and we simulate the faulty model with respect to this initial test suite, and we obtain a set of simulation traces. Once we have these simulation traces, we monitor the simulation traces with respect to the specification, the requirement. And then we obtain two sets, the passing test and the failing test. So we choose only the failing test, we take only the failing test, and then what we do, we use a global optimizer that basically explore the space of the input of the test to find another test that is there's a distance, an Euclidean distance, as minimal as possible with the failing test, but is now making the oracle passing the test. Then with this, we basically generate a set of tails of failing tests and passing tests. Once we have this set of failing tests and passing tests, what we do is we simulate the faulty model and we record all the internal signal using both failing and passing. We obtain simulation output and we do trace analysis of this simulation output to identify what are the suspicious signals that are responsible to make the test that in one case is passing to be failing in the other case. Once we have done that, we map all the suspicious signals to the model block, and we provide to the engineering a list of suspicious signal and model blocks. Okay, so this is basically what happens. We have a passing test and a failing test. Then what we do is we try to analyze what is the difference between the passing and the failing test, and when the difference started to occur. So, for example, here we say that we can see that at timestamp 3, we have that S1 and S2. First S1 is changing and then S2 is changing, but all the other remains the same. So in this case, we will provide suspicious signals S1, S2, and we will map these back to the block that are responsible for this signal. So we perform more extensive validation for this approach. Basically, we use 3 different benchmarks, and we generate. We have a special tool for fault injection, for automatic fault injection, that generate many different fault models, some with 1 fault, 2 fault, or 3 faults inside. We generate the initial test suite using active random testing, and we use RTMT for producing from a monitor from the STL certification. We compare with our previous tool, CPS debug. What we saw is that basically we have a better fault localization ability because STL-FL is reducing the inspection to 80% of the signal regardless of the number of faults, and is more effective than CPS debug by 43%. And we are able to work well also with multi-fault programs, while CPS debug sometimes is misled by multi-fault programs. And we have improved efficiency by having, for example, 25 seconds in average, by having 32 minutes in average to 25 seconds in average. Okay, I conclude with the main takeaway message. Basically, we present 2 different approaches, one CPS debug, and the other one is STL guided FL. In one case, CPS debug is more expensive and less effective, but because we use properties like specification language and the property mining techniques, the explanation that we provide is more explainable. It provides more explanation. While STL guided FL is fast and effective, however, we provide to the engineering only a list of suspicious signals that does not. I mean that it's less it has a less explainable power with respect to CPS advanced. I would like to conclude by thanking all the collaborators with whom we have developed these two tools that I presented you here. Thanks for the attention. Can you hear me?
Yes.
So you have any question?
Really wonderful presentation. Very nice work and very well presented.
Oh, thank you.